Imagine launching a space probe 45 years ago and having it still function in regions it was never designed to explore, operating well past its intended lifespan. This is the astonishing truth behind NASA's Voyager 1 spacecraft, the farthest human-made object from Earth. Launched in 1977, this ambitious mission has transformed our understanding of space, stretching the limits of technological durability and human achievement. Even more remarkable, this spacecraft, now billions of miles from Earth, continues to transmit data using technology older than the cassette player. Despite its antiquated systems, Voyager 1 has recently made a discovery that has captivated the global scientific community, challenging long-standing beliefs and igniting fresh curiosity across the globe. So what exactly did Voyager 1 uncover in the remote depths of space, and what implications does it hold for humanity? To understand this breakthrough, we need to revisit a pivotal chapter in the history of space exploration. During the 1970s, NASA embarked on two of its most legendary missions, thanks largely to the ingenuity of Gary Flandreau at the Jet Propulsion Laboratory. Using only a pencil and the basic engineering tools of the time, Flandreau charted an extraordinary route through the outer planets, Jupiter, Saturn, Uranus, and Neptune. He realized that during the late 1970s and early 1980s, a rare planetary alignment would occur, an event that happens only once every 176 years. This cosmic arrangement formed a kind of celestial necklace, enabling a spacecraft to gain momentum via gravity assists. These slingshot maneuvers would allow the probe to accelerate by borrowing energy from the planet's orbits, drastically reducing travel time to Neptune from 30 years to just 12. Recognizing this fleeting opportunity, NASA acted swiftly, launching two nearly identical spacecraft, Voyager 1 and Voyager 2, just 15 days apart in the summer of 1977 to take advantage of this rare shortcut. What no one foresaw was that these twin explorers would go on to break every record in the annals of space travel. More than 4.5 decades later, both Voyagers remain operational, continuously sending back invaluable data from the outermost regions of the solar system. These spacecraft have become the most distant human-built objects ever, reaching far beyond the goals of their original 4-year missions. They've evolved into pioneers of interstellar space, delivering unexpected and transformative findings. From their earliest flybys, the Voyagers revolutionized our view of the outer planets. They provided humanity's first close-up observations of Jupiter and Saturn's moons, revealing astonishingly active and diverse environments. Who would have predicted volcanoes erupting on Jupiter's moon Io or the intricate ice landscapes of Saturn's moon Enceladus? These findings reshaped our understanding of the solar system and suggested that even remote frozen moons might possess conditions favorable for life. Voyager 2 went on to achieve a unique distinction. It remains the only spacecraft to have visited Uranus in 1986 and Neptune in 1989. These flybys unveiled never-before-seen features and surprised scientists with data from parts of the solar system previously untouched. Now over 14 billion kilometers from Earth, these car-sized spacecraft have consistently exceeded expectations. Their groundbreaking paths began with unprecedented gravity assist maneuvers, including a careful flyby of Venus on the way to Jupiter, a feat only previously accomplished by Pioneer 10 and 11. They navigated the treacherous asteroid belt, enduring hazards few spacecraft had faced before. Powered by onboard computers with a mere 69 kilobytes of memory, far less than even the simplest modern smartphone, the Voyagers had to autonomously manage deep space navigation, scientific observations, and data transmission. Collected data were initially stored on 8-track tape recorders and sent back to Earth via 23-watt transmitters, comparable to the power of a household light bulb. Each spacecraft carried a 12-foot high-gain antenna to maintain communication across unfathomable distances using light-speed radio signals. However, maintaining contact became increasingly difficult as the distance between Earth and the spacecraft grew by 3 to 4 light seconds each day. Eventually, Voyager 2's transmissions took over 18 hours to reach Earth. Compounding this challenge was the rising tide of electromagnetic interference from Earth-based sources, televisions, radios, and smartphones, all making the detection of these faint signals increasingly complicated. Despite these challenges, the Voyagers continued to deliver stunning scientific revelations, particularly as they neared the edge of the solar system. They helped redefine our understanding of the distant and mysterious Oort cloud, a vast halo of icy bodies gravitationally bound to the Sun and stretching halfway to the nearest star. Although neither spacecraft has reached the Oort cloud, they achieved a major milestone by crossing the heliopause, the boundary where the Sun's solar wind yields to the interstellar medium. Scientists originally estimated this boundary to be about 50 astronomical units AU from Earth, prompting NASA to extend the Voyager mission. However, the transition into interstellar space did not unfold as expected. Researchers had predicted a noticeable rise in cosmic rays and a distinct change in magnetic field direction, marking the shift from the Sun's influence to that of nearby stars. On August 25, 2012, Voyager 1 officially crossed the heliopause, registering a marked increase in plasma density, confirming it had entered interstellar space. But strangely, the expected shift in magnetic field direction was absent. This unexpected finding suggested a far more complex and blended boundary between the solar system and interstellar space than previously thought. Instead of a sharp divide, the heliopause appeared to be a turbulent mixing zone where solar and interstellar particles interweave. Voyager 2 followed suit in November 2018, crossing into interstellar space with several still functioning instruments that Voyager 1 had lost. These tools enabled it to gather even richer data about the surrounding environment, measuring plasma waves, magnetic fields, and cosmic rays. One of the most fascinating discoveries came when Voyager 2 detected faint oscillations in the interstellar plasma, ripples likely caused by solar outbursts that had traveled outward for months. This revealed that the Sun's influence extended much farther than previously believed. The spacecraft, running on dwindling power, continued to operate thanks to meticulous energy management by mission engineers, originally powered by 3 radioisotope thermoelectric generators, RTGs. The Voyagers now receive only trace amounts of electricity. Mission controllers have had to disable non-essential systems, including heaters, leaving instruments exposed to freezing temperatures they were never meant to endure. Remarkably, many of them still function. Among the most iconic features of the Voyager mission is the Golden Record, a 12-inch gold-plated copper disc affixed to each spacecraft. Conceived by a team led by astronomer Carl Sagan, the record includes greetings in 55 languages, a selection of global music, natural sounds, and 115 images depicting Earth's diversity. Though the likelihood of alien contact is minuscule, the record remains a powerful symbol, humanity's cultural ambassador traveling across the cosmos. The recent discovery that startled scientists relates to a persistent hum detected by Voyager. One in the interstellar medium, a faint ongoing plasma wave indicating that space between stars is not as silent as once thought. This background noise offers clues about particle density and movement, suggesting that interstellar space is a far more dynamic and interactive environment than previously imagined. Each stream of data returned by these ancient spacecraft enhances our knowledge of the galaxy and helps shape plans for future deep space missions. But the Voyager saga is more than just a scientific triumph. It resonates on a deeply human level. These probes were launched during a time of limited computing, power, and uncertain communication technology. That they have endured so long speaks volumes about the vision, dedication, and ingenuity of their creators. The engineers and scientists currently managing the mission often express an emotional connection to these distant travelers, a sense of duty, reverence, and even affection. Looking ahead, the mission's future is bound by physics. At some point, the RTGs will no longer produce enough electricity to power any instruments, and the Voyagers will fall silent. They will continue to drift through interstellar space, mute but eternal. In about 40,000 years, Voyager 1 is expected to pass within 1.6 light-years of the star AC plus 793888, while Voyager 2 will come near Ross 248 around the same time. Though the odds of an encounter with another civilization are vanishingly small, the thought of these man-made emissaries continuing their voyage, perhaps long after humanity itself has vanished, carries a poetic resonance that transcends science. The achievements of the Voyager mission remind us that exploration is not solely about immediate returns. It is about curiosity, courage, and the unyielding drive to understand our place in the universe. As Voyager 1 continues its journey through the cosmic abyss, It carries not only scientific instruments and recorded sounds, but the enduring legacy of a species compelled to explore the unknown.